Hello, everybody. Thanks for being here and thanks for having me today. I have a story for you, so let's get started. Each great story has a great villain, or most of them do have. So, like Star Wars, they have this dark guy. Like Batman, they have this other guy, Joker, I guess. So my story, I aimed for it to be no worse, and I have my own villain, which is this one. So as you can tell, I'm here from Wrocław, and on the right-hand side, if it's not very clear, this is a derailed tram. If you're from Poland, you might have heard a word about that or two. So my name is Michał. I blog about Scala. I do OSS from time to time, and I'm a senior software engineer at SiriusXM, where I enjoy writing Scala 3 in production, doing some crazy stuff with macros and everything. So if you want to learn more, catch us up at the booth. But those are important parts, but there is one more important part. I have a very bad luck when it comes to public transportation. And this is my story with FS2, type level stack, and some trams. So to give you a highlight, because not everyone knows my adventures with trams, I was giving this talk back last year in Wrocław, and basically I wanted to share like a picture where the venue is with some friends of mine, so I went to Google Street View, and this is what I found. Yes, the tram is hiding the entrance, so that's the hint how it works. Or at the other day, when they took stopping at the bus stop too literally. So those things happened to me from time to time. So I started questioning myself, maybe it's about me, and probably it is. But this is a good excuse to ask a question, how slow is my tram, and to find out with Scala, right? So let's try and find it out. So the plan would be to find a data source of like positions of trams and buses, then fetch some data, then fetch some more, calculate the differences between their positions, and produce some statistics. They might not be very precise, but it's not the point. The point is to write some Scala, right? Okay, so moving on to the first point. We have this interactive map that shows you the positions of public transportation, like buses and trams, and it looks like that. So I figured they update it on the go, live. You can select like a bus line or a tram line. So they should have an API for that, right? So I figured they must have an API documentation, right? Right? They didn't. So I had to go to the inspector, copy the request. This is like a curl request that has some bunch of like things that I need to send to receive the info. And voila, we have some data. So let's dig through it very quickly to learn what we are working with. So what does that data mean? First thing was the name. So that's quite obvious. It's the line number because it's a name, right? Then there is a type. That's obvious, tram or a bus. Y, which I figured must have been a latitude. X, which is the longitude. And the last but not least was K. I had no idea what the K was, but I went through the data and it seemed to be like unique across like unique identifier of the result, and it would be assigned to the very specific like train or a tram or a bus on a specific line. So this is like our key, right? Cool. We have some data. We might have chosen like a better data source, but who cares? We have something. So next to fetching and parsing, right? So let's see some Scala code. What do we need to send? We need to send an HTTP post request, right? This is the input that we need to give it. So this is some sort of like a map you can think of. This is like a map that has a list of buses and list of trams, basically. We need to specify the content type, which is like form URL encoded, and we expect to receive JSON. How do I know that? Not from the API documentation, right? Okay, so we're going to use HTTP for that because we're on Scalar Conf after all. So this is like something to begin with. So there is this API URL that I just figured out by looking at the inspector, and something to prepare the payload that's as they expected, because we don't have control over it. We have to generate something that's compliant, right? Then comes the return type with the K, because this is what to return. And nothing very fancy about that. You've seen this derives word, I guess, on 2 presentations already, so I'm not diving into derivations. This basically means that we can just turn JSON outputs into those case classes. So to the more interesting part, we have this HTTP request. So to request a list of positions of those vehicles, we will use some sort of backend. Those of you who are not very familiar with this, backend is the engine that executes your HTTP request, basically. The other inputs are the list of buses we want to see and the trams that we want to see, which are strings because why not? Then to the body of the request. Also, please notice that we are using I/O as the return sort of effect. Who is familiar with I/O? Okay, perfectly. Most of the room. So basically, this is like a promise that we will do something, but we will need some other runtime to execute it. So that's enough to understand it. So we are doing a post request towards this URL that we have specified. We use this payload from the slide before to generate actually body of the request. Then goes the content type. And we say that we expect a list of records because the return type is JSON and we expect to receive a list of records. We send it using a backend. We don't care about any other metadata, so we only care about the body. And in case anything goes wrong, like we're rate limited or anything, we just rethrow the error because this is a very simplistic approach. Okay, so we have this piece that returns an I/O that doesn't really work. So let's try it out. To try it out, we need to execute the I/O that we have basically generated. And we need to spawn this HTTP backend because I only said that we're going to require one, right? So we're going to write a simple app. It's there. It's simple, right? So in Cats Effect, you can basically create like a main class that extends some provided trait, and the only thing you need to do is to implement this run method. You need to provide an I/O, and it will handle the stuff around executing that. So let's plug our logic in. So we have specified some trams and buses just to have something to work with. We are creating this FS2 backend and use it with this request method. So basically, we obtain the backend, we plug it into the request method along with the buses and trams, and we print out the results. So we should be good to go because I/O println returns you an I/O of units, so that's compliant in terms of types. So what's the result? Well, using Scala CLI, we can see that there is a bunch of results that look like promising, right? So good. We have the data, but we also have K. And I don't know about you, but I don't like to leave my code like this, so I come up with the idea to just like abstract it. So we're going to try doing like separation of concerns, right? We will implement a very simple, like a service or algebra, if you will, that when executed will provide you a list of buses and trams positions. So notice that we are returning a vehicle type. I know the name is not the best, but it's short and it makes sense on slides. And we don't want to get rid of those internal representation, be it K or anything. We want to work with something abstract. So yeah, let's define the vehicle as something meaningful. We have a line name, we have the time of the measurement, we have the position, which is defined as just like another case class that contains two doubles and some enivals for aliasing ID and line name. Okay, so we know where we want to get to. Now, our code currently looks like that. So we have this basically request method that does the heavy lifting. How do we plug it in? So we basically need a method that will create an instance of this vehicle service. And we need to like come up with the implementation. This is not a live coding session, so I can just switch slides. And you can see that we basically execute the request along with capturing current time because we need the time of measurements that is not provided by the API. And we do simple mapping because responses is just the list of records, right? Those with the key. So now we produce those vehicles plugging in the values into the right case classes. Nothing really sophisticated. And we have an achievement. So we separated concerns and we got rid of K. Perfect. We have something to work with, right? We will work with those vehicles, and from this point further, if you want to try it out and like implement it for your own city, you basically need to implement this part, and the rest of it will be agnostic of the API below. So that's another benefit. One last thing. since we have those vehicles and we will be basically measuring the distance they covered, we need to have a method that will calculate the distance between one vehicle and the other, right? So I was very, very lazy when writing this talk, and I just shamelessly copy-pasted that from Stack Overflow, so I'm not going to discuss that. The idea is that when you have two measurements, you can do something like that, okay? So you have a measurement, you just call the distance, and this thing produces the distance in meters, so that's something to work with further, right? Cool. This was something just to build the ground, and let's go back to the plan. Where are we? So we have basically fulfilled the first 2 points that enable us to basically do something interesting and calculate stuff. Now we need to use this API that we have just created to fetch some more data, calculate the differences and stuff further. So here come the streams. Who knows what a functional stream is? I expect at least 10 hands raised. That's much better. Okay, so just a very quick recap. Functional stream, you can think of it as like a sequence of data elements that can be computed like in a lazy fashion on demand. Thanks to being calculated lazily, it can be infinite, because if it was eager to calculate each element, you would get out of RAM very quickly. It can be asynchronous. This might be mysterious for newcomers, but this means it can basically evaluate IOs on the go, right? So if we have this list method, we would be able to evaluate it within a stream. And it has a very powerful API of combinators, which we are going to learn right now, just to give you a hint of what you can do with application modeled with a stream. So let's do an exercise. Please rise up, and we're going to make pumps. No, kidding. Exercise is going to be about writing very simple programs. So we will create infinite stream that produces natural numbers, right? Then we will filter out, so we will only keep the odd ones. Then slide through them as, we take the first 3, then the next result is just by shifting the window, as in the old-fashioned like calendars, when you had this window that showed you which day it is, but 3 days long for reference. We have those groups. We want to sum them up and produce first 10 results. I won't ask you to imagine how it would look like in like an old mutable fashion way, because it would make your heart explode, but let's move on to the stream implementation. So this is it. You build a stream by iterating. You start from 1, and then you provide a function that basically creates a new value out of the previous one. So you have 1, then plus 1 is 2, then plus 1 is 3, so on and so forth. Now, filtering, we want to keep those that don't easily divide by 2. Now, for the sliding window, this is a very convenient API. I mentioned that you have very rich API. This is it. You want to slide, you have a method to slide. Clear. Now, since we want to add all those elements within the slide, the sliding produces a chunk. So think of it as a glorified array of elements. If you did slid by 3, then you have 3 elements in the array to work with, basically. So we summarize the chunk, and we can take 10. But if we changed our mind and wanted to take 100, it's just about changing this value. And it's great. It's very declarative, as you declare your intentions rather than the way you want to produce the values, right? But you might ask how it works internally, because this is very mysterious, and this is a thing that even senior developers can struggle with. So there is a plug of a great library of Aquascape. Shout out to Zainab. And let's see how the execution model basically works. So we have a stream, and you will notice that on the bottom we have this very last thing that we called. On the top there is this iterate, so very first thing that we did. So let's move on from left to right. The first thing that the stream would have produced would be number 1, because we start with natural numbers, right? Then the stream would filter the numbers, only keeping the odd ones, and 1 works, right? So the next thing to do would be to slide, gathering like 3 elements, but we only produced 1 element. So at this point, we are not going any deeper, if you will. We move on. So iterator will produce 2, but 2 is not odd, so we like ignore it, we don't go further. We then iterate, we produce three matches, but we only have 2 elements now, so we don't slide yet. And so on. 4 is not odd, 5 is odd, we have 3 elements, so we can slide now, right? So we do sliding, and we produce this chunk 1, 3, 5. That makes sense, and since we don't filter or anything, so then we can summarize the chunks, so we add them up, there is 9, and since we are taking 10 elements, and we have took none as of yet, so we take the 9. And the thing goes on, so we can now move on to the iteration. 6 is not odd, so we don't take that. 7 is odd. 7 matches the filter, and now we can move. We are moving just by 1, right? So we take 7, 5, and 3, we add them, we produce. So you can imagine that any further calculation would look like this, right? So it's very this narrow kind of structure that will produce values and finish once we have taken 10 elements. So I highly encourage you, even if you are experienced with Stream, to try this library just to boost your understanding of how streams work. Hopefully that explains something of the execution model. Now let's move on to the real use case, since we are now all experts on FS2, right? What should the application really do, like on the very abstract level? So we want to, upon n seconds, not to get into rate limiting, upon each seconds we want to call the API for the new data, right? Once we have the data, we want to compare it to the previous result and calculate the differences between position to, basically call the distance method. And then after a fixed amount of updates, we just gather those differences out and calculate some sort of statistics. So just to give you like a visual understanding of what's happening, there's a timeline, and this is what's going to happen. First of all, we're going to execute this API call, and we will produce, think of it like the map of the positions, right? But we have nothing to compare with, so moving on to another API request. Once we have 2 results, we can compare them and calculate the difference. So this is what we do. We will produce this like a list of movements of specific vehicles, right? And now, sliding, as you can imagine, by 2, we will execute another API request and produce another diff. That makes sense, hopefully. So let's think of how can we implement that in terms of FS2 streams. So we will have a stream that is infinite, because we don't want to be fixed at any number of measurements as of yet. It acts on every n seconds. It will use the API that we have just implemented a while ago, the one that produces the vehicles rather than records. It will need to join the results by ID, because the results are not sorted, so you need to look up by this K underneath to have the matching vehicles. After that, we will just calculate the distances and build something that we can then read and calculate an average or something. But let's go very step by step. So let's list the vehicles every n seconds. And as I said, FS2 gives you a rich set of combinators, so we can do this with 2 lines of code. So we want a fixed rate start immediately. Basically, this is all our requirements. It will be executed every 7 seconds at this example. And upon each invocation, we will execute this vehicles list. So we basically have a stream that upon each 7 seconds will produce a list of vehicle positions. Easy, right? So how much of a plan we have covered? Well, half of it. So we have an infinite stream. We read upon each n seconds, we list the vehicles. Now to the hard part. We need some joining, some distance calculations, so I will need to be very focused for a moment. So step by step. How does it look like? So I was talking about the sliding method, and as you've seen on this visualization, we will need to have always 2 measurements, right? So we do slides over 2 subsequent measurements, and we want to calculate the difference between those lists of vehicle measurements, right? So to do that, we need to know how to calculate the vehicle position difference to start with. So this is like a helper case class that I have just created. It's basically identifier of the line, and then how long did it take to move and what distance did it cover. So if you want to calculate this vehicle position difference, you basically take 2 measurements, You calculate how much time elapsed, what was the distance, and produce the case class. It's nothing sophisticated. This is just to make the tapes sane, right? This is easy. Now that we have a mean to calculate difference between two vehicles, we need to do it on the entire sets, right? So this is what the API returns, and this is what it returns after 7 seconds, and we need to produce like sequence of position differences. So if you recall the image, this is the part that we want to implement right now. And as bad as it seems, it's just this. So we have like one snapshot, you join it, whatever that means, with the other, and then call this between distance, right? So sounds easy, but the join is something that I had to implement myself. It's non-optimal, so don't judge me. It just goes over first like a collection, then tries to collect matching by ID, and that's all. Nothing sophisticated. You could do it more. You could make it faster, but that's your homework. So where are we again? We have just explained how to calculate the differences between the entire like results of the API calls. And again, thanks to the separation of concerns, this is agnostic of the underlying API. So this is something that you don't basically have to care of if you are implementing for yourself. And now let's go back to the plan, see where we're at. So we have something that fetches the data, calculates the distances, joins them. So the only thing we need to do is to produce some statistics. So let's go step by step again. This is our stream. We finished at this calculation of diffs previously, so we added those parts. And for those of you seasoned with FS2, you know that we are finished right now because we compiled and we produced some value. But the important part is here, so we decide to take a specific number of samples and basically fold the stream. Do you recall fold command or method? Okay, I guess that's less hands done with the FS2, but okay. So with fold, this means that we want to go over each value and somehow like modify the accumulator based on that, right? So we start with like an empty map, and we execute summarize on this previous value and the diff, right? So the summarize is defined as like this. So you have previous summary, which is this initially empty map, and then this sequence of vehicle position differences, which is something that we produced previously. It's not very like sophisticated. We just want to make sure that we match the line ID on the left-hand side and produce the stats. So we just have the meters distance and seconds duration. And all we need to do after that to combine two maps is to call monoid. And I promise I have slides for that, but I know I'm not going to make it, so catch me at the corridor, I can finish that. For those of you who worked a bit with cats, I guess you already know what happens underneath. So yeah, this is the entire like application that has so many like requirements, contacting the outside world, relying on external APIs, doing some sort of calculation, so on and so forth. And the one takeaway I want you to take from this point is that you don't always need to like produce another web application or something that consumes like one stream and produces to the other. Streams can be used in very different situations, and perhaps they are just good tool of thought for you to like reason about the program that you're writing. But since we have only produced a stream, we need to use it somehow in the main. So let's go for that. We have this main program, and it looks like horribly large, but you can recall the run is almost intact. We just added a program that executes the stats and does a bunch of print lines. I don't want to go to the details. I'll show the code later on. But I already executed that one yesterday morning with the interval of 9 seconds because I was getting really pushed back from the API. I took 72 samples, which is roughly 10 minutes. And let's see how it went. So for the buses, the fastest bus in the city of Wrocław was number 149, which was 20 kilometers per hour. The slowest one was 14.4. And this is not very bad because trams were slower. The fastest tram was slower than the slowest bus, which was like 13-something kilometers, and the slowest was not very far from that, 11.4. So the average is not very impressive, right? So therefore, to ask the question that I set for myself at the beginning, how slow is my tram? Well, it's slower than a bike anyway, so this is what I'm choosing. But we have learned something on the way, and this is the great outcome. So data is not necessarily easy to find and might need some refining. Separation of concerns is a good thing to do, especially considering the benefits that you may have when refactoring this one. Streams are a nice way to model business logic and also a good tool of thought. So always consider writing a stream just to give yourself an idea how you can implement the thing you're working with, and Aquascape is real fun. Thanks again, Zainab. And thank you for listening. I hope you weren't bored. Thank you.